Hello, my name is Kyle Van Sice. I'm a graduate student at Iowa State University in architecture. Today I want to present to you my poster research for the Design, Social Media, and Technology to Foster Civic Self-Organization conference in Hasselt, Belgium, taking place May 21st to the 22nd. Specifically, my poster is addressing the third track, how can the impact of design, social media, and technology on civic self-organization practices be documented and evaluated. This research focuses upon the existing architectural design process and the associated fidelity and speed at which information and intelligence is exchanged between the large number of disparate actors involved. I call this fidelity and speed of information and intelligence feedback frequency, and I then suggest that as it increases, so does the resulting richness of design potentials. I would like to begin by first analyzing the current nature of design practice. Building design and construction is a complex process whereby no result is likely ever the same. This requires a diverse, multidisciplinary range of experts who must come together in a kind of singular pursuit. This range encompasses everything from community activists and local authorities to engineers, architects, and contractors, very few of which have similar modes of communication. The routines that result from such a fractured process are often artifact-based as a means of creating some sort of standardization in an attempt to increase productivity. However, this prevents prototyping and testing of potential solutions as the routines for development are linear and feedback is thus limited. Solutions are iteration-based instead of emergent. This diagram attempts to map parts of the interaction that takes place during the process and shows how these actors become relegated to collaboration almost strictly within their discipline, and thus communication between disciplines is more so coordination than it is generative. The increased prominence of computation and technology in architecture has the potential to not only increase the productivity and usefulness of our tools, but also to radically change the nature of these existing routines. The introduction of generative and algorithmic methods within the architectural design process has afforded designers a significantly increased level of knowledge and control over their work. These methods offer the capability for near instantaneous feedback, allowing for the rapid evolutionary testing of ideas, thus expanding the potential landscape of fit solutions. Parametricism is a computer-aided drafting platform that allows for the inclusion of signal feedback as generated by any number of actors to be contained in an extremely flexible format. This facilitates the emergence of evolutionary processes in design as possibilities can be continuously generated, analyzed, and re-examined based upon their response to the given constraints. These platforms become both tools for developing and defining the dimensions of search space, as well as for choosing fit solutions that emerge from it. I would now like to illustrate the impact of these platforms on feedback frequency using the example of the building utilities assemblage, that is, the collection of mechanical, electrical, and plumbing services within a building. According to Deleuze and Guattari, an assemblage is the structuring or constructing of disparate elements into a singular whole whose result is greater than simply the summation of these parts. This sees a system as not divisible and element-level performance as independent of system performance. This diagram shows this assemblage and suggests that the principal goals of the utility design process is to find a way to combine any number of these parts together in a way that meets the respective performance requirements of occupancy within the broader built space. You can see that each element has a respective performance and size factor, which correlates to a broader assemblage performance and size factor value. Existing means of determining how these parts come together lies in the realm of coordination. Once the architect has designed the overall layout, utilities engineers begin designing their respective systems. Once they have completed this work, they come together in a series of coordination meetings whereby they determine where conflicts and collisions take place between the parts. Rerouting then occurs and the initial solution is iterated upon until all conflicts and collisions are mitigated. However, due to the lower level sophistication of this method, errors are common and further rerouting often takes place in the field once the assembly is begun. This inefficiency is the result of flow frequency feedback, and performance and size factor criteria are ill-considered in the iteration period as the only goal is conflict resolution. This column represents this slow feedback frequency. As you can see, the resulting landscape is of a singular solution, the one which is iterated upon, and you can see here the resulting solution as it might be built in the field. You can see that there are a lot of rerouting elements and that these inefficiencies exist in these locations. Yet, with the implementation of a complexity-based approach, one could expect a very different design process to emerge. The near instantaneous feedback condition considers these factors from the beginning of the design process and uses them to breed a number of potential assemblies of these parts. This is represented in this column. A model is built at the outset of design, and the thermal, fluid, physical, and mechanical phenomena the system is designed for are directly fed into it, so the design can be optimized for given loads and size clearance requirements, as well as checked against code specifications. This ensures the model's intelligence, and since it is also parametric, and thus allowed to flex and create different structures, coordination now becomes somewhat automated and instantaneous. One would expect a number of potentials to emerge from the resulting search space, or landscape, which are free of conflicts and collisions, and provide varying levels of fitness in the interaction between, in this case, performance and size factoring. Most importantly, such a workflow would allow designers to continuously create, optimize, engage with others, and re-examine and recreate. This diagram maps the resulting design process. One can now see a breakdown of traditional hierarchy and discipline segregation, as all are now communicating with a common language, that is, an intelligent, flexible, generative central model. Collaboration is radically improved, and those who normally might not have a prominent voice in the design process now do. While the potential for complexity theory to change architecture as a discipline is quite compelling, there are still many obstacles to overcome. The tools, which serve as platforms for parametrics and genetic algorithms, must be sufficiently user-friendly so that a wide array of designers of varying skill sets could communicate and utilize them at an even level. If not, collaboration actually becomes more difficult and feedback begins to lag as dynamic routines require the intense involvement of all stakeholders. These platforms must also have the capability for customization to meet the work styles of individuals. This flexibility is key to breaking free of an artifact-based system by which all must conform to the same mode of creation. Further next steps must consider the pedagogical shift in architectural education required to accommodate such a shift in practice. I would like to thank Sharon Wall for introducing me to the theory of complexity in architecture and for assisting me in this research. And I would like to invite you to contact me with any questions you may have at the given email address, vansiceK@gmail.com. Thank you.